Okay, so this is the outline for the supplementary note. So first we will talk about the Maxwell equation in free space, and then we will derive the wave equation from the Maxwell equation in free space, and then we will try to solve the wave equation. Of course, it is a partial differential equation, but actually this specific type of partial differential equation is solvable and not so difficult. But generally, most of the partial differential equations are difficult to solve. But here, yeah, for wave equation in free space, well, we can have a elegant solution to it. And then, yeah, we can see the solution to the wave equation in free space is actually the electromagnetic wave. Okay, so in the last chapter, we know the differential form of the Maxwell equation as this one, the Gauss law, the divergence. The divergence of E is rho over epsilon naught. Divergence of B is 0, and then the curl of E is negative partial B partial T. The curl of B is mu naught times J plus epsilon naught. This is the displacement current. This is the proper current. Okay, so here we make an assumption that the EM wave is in the free space. Of course, you can still derive the wave equation in the space that has charge and current. And actually, last year I make the derivation in the final exam because I just saw it on the lecture, but there are only few students attending the class, so I just announce it on the class that I will make this derivation in the final exam as a bonus problem. Okay, so but yeah, this year it will not be in the final exam. But yeah. Okay, so free space means there is no charge density. So rho is the charge density here, and then J is the static current. J is the static current. So here we assume that the rho is 0, and the charge and the current density is a 0 vector. So this is 0, this is 0. Okay, so it simplifies the Maxwell equation a bit. Okay, so this is the Maxwell equation in free space. The divergence of E and B are all 0, and then for the curl of E, curl of B, so this is a negative partial B partial T, and here mu naught epsilon naught, and then times partial E partial T. So they look quite symmetric because for this case we have a J here. It's not so symmetric. And here it's not so symmetric. This is 0, this is a non-zero value. But in free space, the Maxwell equation look quite symmetric. Both of the divergence of the E field and B field are 0. Curl is a partial derivative of the other field. Of course, we have a negative sign here. And then actually we need a identity called the curl of curl identity. So it is like the curl of a curl of F. F is a vector field, so it will be like this is a gradient of the divergence of F minus, this is called the Laplacian. The Laplacian is like is actually as the gradient dotted with the gradient, So this is the Laplacian of F. Okay, and you can imagine that this is gradient dotted with the gradient. So it is like a scalar operator. A scalar operator operates on the vector. So this is still a vector. And then here, the gradient, I mean the divergence of the vector field become a scalar field, and then taking the gradient, it becomes a vector field again. So this is a vector field, this is a vector field. And here, curl of F is still a vector field, and then the curl of the vector field is still a vector field. So vector field equals a vector field minus another vector field. Okay, we don't try to prove it. If you don't believe, you can try to use the definition in the previous supplementary note, and then you just plug it in, and then the calculation is not that difficult, so you might be able to verify it. Okay, so we just pick it and use it. Okay, so first of all, this one is the Faraday's law. This one is the Faraday's law, if you still remember. So this is the curl of E, and then negative partial B partial T. So if you only remember the integration form, it is like integration of E dot ds equals negative d phi b dt. So you can see how they match each other. The phi b becomes a B field, and then the original derivative becomes a partial derivative, and then here becomes Okay, so this is the Maxwell's law. This is the Maxwell's law, or the Ampere's law. Okay, so this is the curl of B equals mu naught epsilon naught partial E partial T, and then we also need the Gauss law for the electric field. We don't really need the Gauss law for the magnetic field in this derivation. Okay, so here F is an arbitrary vector field, so we pick F to be E. So we have a so we have a curl of E equals gradient of a divergence of E minus Laplacian of E. Laplacian of E. Okay, like this. So we can try to take the curl for this one. For this one, we take the curl. We take the curl on both sides. So on the left side, we have curl of E. So which matches this side. Okay. And then, of course, we need to take the curl on the right side. And then we try to substitute the order for this partial derivative and this derivative. This is something like a derivative. So we put this one inside the partial derivative with respect to time. So we have negative partial T here, and then we have a curl of B. Okay. So we get this one. And then here, this one here is actually this one. So we have a gradient divergence of E minus gradient of E. So maybe I can just put some. I can just put this one. Just put this one here. Just put this one here. So this side is actually this one. Okay. And on the right side, we have curl of B. So curl of B, we can just substitute with this one. So we can have this one plugging into here. And actually mu naught epsilon naught are constant, so we can just put it out. And then we have a negative sign here, and then partial E partial T putting here. So we have a second partial derivative of E with respect to time, like this. Okay, so and finally we have gradient of E. So we can just plug in here. Gradient of E, sorry, not gradient of E. This is divergence of E is 0. So we just plug it here. So it becomes gradient of 0, which is 0. And then, so this one is nothing but 0. and both sides we have a negative sign, so it becomes positive. It can become positive, and then it looks like this. So this is the wave equation. This is the wave equation for the E field. So we have the Laplacian of E equals mu naught epsilon naught. Partial is a second partial derivative of E with respect to time. Okay, so this is like the derivative with respect to the space domain, and then this is the derivative with respect to the time domain. Okay, so this predict how the E field is changing. When the E field is changing with respect to the x domain and with respect to time, and then it will start propagating over the space. Okay, so this is the first wave equation, and then for the second wave equation, we need to make use of the Ampere's law, the Faraday's law, and the Gauss law for the magnetic field, Gauss law for the B field. Okay, so here we try to take the gradient. We try to take the gradient on both sides. Take the curl on both sides. So the left side will be curl of B, and then the right side we also put this one inside the partial derivative. So we have mu 0 epsilon naught, and then partial t, and then here we have a curl of E. And here we also have curl of B equals gradient of divergence of B minus Laplacian of B. Okay, so this is the right side. We have a gradient of a divergence of B minus Laplacian of B on the left side, and then on the right side we can just plug in this one right here. Okay, so we have a negative partial B partial t. So this negative sign can be putting out. We have negative mu naught epsilon naught, and then original we have a partial B partial t, and then we have an other partial t. So we have a second partial derivative of the B field with respect to time. Okay, so and similarly we have this divergence of B equals 0. So this is 0. Okay, and it turns out that this term to be 0. Okay, so in that case, similarly, we have negative sign, so we have plus. So it finally looks like the Laplacian of B equals mu naught epsilon naught second partial derivative of B with respect to time. Okay, so this is the second wave equation, and you can see this is the first one. This is the first wave equation. Okay, and then this is the second wave equation with respect to the B field. So these two wave equations look exactly the same, except this is E field. This is B field. All the other part are the same. Okay, so actually we can try to solve this wave equation to get the solution, to get the EM wave solution. Okay, so here this is gradient of E, the Laplacian of E equals mu naught epsilon naught, and then second partial derivative of E with respect to time. Okay, so actually for the wave equation, I suppose in chapter 17 or whatever chapter, I don't really remember whether it is covered in physics 1. But actually for the wave equation, we don't really care about what is this thing. And then for the wave equation, it is like we have a Laplacian of something equals 1 over v. Laplacian of something, maybe just write it as x. Maybe not good to be x. Maybe just f equals 1 over v squared times second partial derivative of the f partial t, something like this. So we have 1 over v squared here. This is the speed of the wave. So first of all, we already get that this v is not v anymore. This is we will call it c. So this is actually 1 over c squared rather than 1 over v squared, because it is for the speed of light. So 1 over c squared equals mu naught epsilon naught. So we can quickly find that c equals 1 over square root of mu naught epsilon naught, which is the 33.3 equation. Okay, so we can actually rewrite these two wave equation like this. We have a 1 over c squared on the right side. Okay, so here actually for the Laplacian, it is actually like partial x squared plus second partial derivative with respect to y, second partial derivative with respect to c. So this is a three-dimensional. In three-dimensional, the Laplacian will look like this. But we can actually just solve the simplest case, which has only the x-axis component. We just, for example, you can just change the coordinate so that the x-axis is pointing to the direction of propagation, so that we only have a second partial derivative with respect to x. And then for solving the one-dimensional case, we only have this term on the left side. If it is arbitrary direction, so the Laplacian of E will look like this. Y z squared, something like this. Okay, something like this. Okay, but here we only solve for the one-dimensional case, and then on the right side, it is ext and then ext here. Okay, so E is only related to x and t. Of course, it consists of the far field assumption, and it is actually the plane wave, 平面波. Actually, in chapter 33, I already mentioned that if you choose a point far enough away, then the wavefront is looking like a plane rather than a sphere, a part of a sphere. And if it is a part of a sphere, then the solution will not look so good. As much as it has a far field assumption, then the wavefront is looking like a plane wave. Okay, so we try to solve this one. Okay, so to solve this one, we need to use the separable of variables. So this is a general method to solve the partial differential equation, which means that if you have a partial differential equation to solve, the first method you try should be the separable of variable. If it works, then congratulations, it works. If it don't work, then it will be horrible. It will be a horrible procedure. You need to try other method to solve it. So this is actually almost the first step for solving a PDE. It might not work, but for some specific PDE it works. So the idea is that suppose this e of xt is the function we want to find. It is a function related to x and also t. And here we try to assume that this ext is the product of two functions. This function only related to the x, and then other function only related to the time. And then they multiply together to form this ext, e of xt. Okay, and then we try to plug in this one into the PDE we want to solve, and then see whether we can get some interesting property. Okay, so that's the point. That's the point of the separable of variables, which means that this function might not be separable. Maybe, for example, if ext equals x squared plus xy plus xt plus t squared, then you cannot factorize it to become exx times ett. In high school algebra, you know, this polynomial is not factorizable. Okay, so this is not factorizable. Okay, so and yeah, we hope the solution is not like this case. So we try this out. We try to plug in this one into the original equation. So this is the ext. So we plug this one here and here. So it looks like this is exx, this is ett, this is ett. So I use the blue color to stand for the function of e related to x, and then I use the green color to stand for the function of e related to t. Okay, so on the left side, it is related to the second partial derivative with respect to x. So t is a constant, so we can put this out. The left side remains this derivative of ex with respect to x for the second order. And here, this is a one variable function, so we can write the original derivative rather than the partial derivative. On the right side, this partial derivative is with respect to the time. So exx is a constant. We can just put this out. So we put this out, and then this derivative to the ett, this function is only related to time. So we can write it as the original derivative, of course the second original derivative rather than the partial derivative. Okay, so we can do something. We can simply divide exx ett on both sides. Okay, by doing this, ett and ett can cancel on the left side. So on the left side we have this term here, and then we have exx in the denominator. Okay, so the left side becomes this one, and then for the right side, exx and exx can cancel each other. So we have this term here. We have 1 over c squared here. We also have ett in the denominator. Okay, so I still use the blue color to stand for ex, and then the green color to stand for et. So here you can quickly see that the left side is only a function of x, and the right side is only a function of time. Okay, so this is the punchline for the separable of variables. We try to assume the function with two variables or even more variables to be separable, and then we try to plug in the original equation, and finally we also separate the variables on both sides, on two sides. The reason for this is that this is a function only related to x, this is a function related to time, and they are equal to each other, which means that this function should be a constant function. This function should also be a constant function. Otherwise, they cannot equal to each other. This is a function of x. For example, if we have a t to be a fixed value, and then we try to vary x, so the value on the left side shouldn't change. So which means that the x should be a constant function. And similarly, t should also be a constant function. So we can assume that both sides should be equal to a. And then we separate the variables. And then we can write this one equal to a and this one equal to a. So we convert the partial differential equation into two ordinary differential equation. Okay. So here we can write the left side equals a, and then the right side equals a, with two ordinary differential equation. Okay, so here, so here we can try to multiply this one on both sides. So we have a times exx, and then we also multiply this one on both sides. So we have a times c squared ETT. Okay, so so here. Okay, so there are three cases. If a is larger than 0, if a is a positive number, then we can just change. This is a second derivative. This is s squared equals a, and then this is the original function. We change it to 1. So in this case, we have s equals plus or minus square root of 8. So we have the solution to be exponential to square root of ax, exponential to negative square root of ax. And then similarly, if a is positive, we have a square root of ac times t, and then negative square root of ac times t. Okay, so and the general solution to the ext should be like a times this one plus b times this one. This is e of x, ex of x, and then e of t will be c times this one plus d times this one. This is et of t. This is not a good solution because this is an exponential function. It will tend to infinity if x is tends to infinity or negative infinity for either one. So it will diverge. And as much as E tends to infinity, we need infinite energy to generate this kind of E field. So this is not possible. So this is not a good case. And the second case is if A is 0, which means that Ex double prime is 0. So it turns out to be Ex to be A plus Bx. And similarly, Et of t should be c plus dt. So it's not good either because if x tends to positive or negative infinity, ext will tend to infinity. This is not good either. Okay, so this is the third case, which is a is smaller than 0, so we can get the sinusoidal solution. Okay, but limit to time, so let's stop here today.